Okay, now we're going to start talking about Gauss's law, which is an application of electric flux, or theory about electric flux caused by a set of charges. Gauss's law is actually a result from vector calculus, but it's applied very well in this particular case. First of all, let me introduce you to another constant. We've talked about in Coulomb's law that the force is equal to K times Q1, Q2 over R squared, and this K is equal to 9 times 10 to the 9th, 10 to the 9th Coulomb meter squared per All right, now we're going to start talking about Gauss's law. Gauss's law is a way to find an electric field in some particular cases where it's a lot simpler to use the symmetry of the system rather than to go ahead and do the horrible integrations that we did before with the discrete charges. Gauss's law is actually a more exact or more correct expression of the electromagnetic field than Coulomb's law. Coulomb's law is a special case that can be derived from Gauss's law. Gauss's law says that if you have a closed surface and you measure the total electric flux that goes through that surface, and the electric flux might be caused by charges that are located inside the surface, or it might be caused by external fields caused by objects outside of the surface. Let's see, I drew these wrong. Field lines go towards the negative charges. Gauss's law says that the total flux that goes into that closed surface is equal to just the charge enclosed in the surface divided by a constant, which we'll call epsilon 0 for right now. I'll tell you what epsilon 0 is in a minute. All right, well, let's see. The flux is no more than at each point along the surface, you measure the electric field and you dot product it with the area. And so this is in some sense a summation of the flux over all of the parts of that area. And in a minute, we'll show you how to do that summation, especially for any general surface. But for right now, let's look at this epsilon 0 for a moment. Okay, epsilon 0 is a constant that's called the permittivity of free space. You remember that when we talked about Coulomb's law, we talked about this constant K, which is equal to 9 times 10 to the 9th newtons meter squared per coulomb squared. Well, epsilon 0 is defined to be 1 over 4 pi K, and it's equal to 8.85 times 10 to the minus 12, and it should have units of coulomb squared per newton meter squared. Okay, so this is one of the fundamental constants of nature, just like the universal law of gravitation, big G, or any one of another, or the charge on an electron, little e. Okay, so that's called the permittivity of free space. The strange name has to do with some historical facts. Okay, so let's see how we can use Gauss's law and this constant to calculate electric fields. So let's suppose we have an arbitrary surface, and I will start off by looking again at a cube that is got one face towards you, and it has 4 faces and a face in the back. All right. Now, what did we learn about the flux in this situation before, when we had a constant field that went through it? When we did that case, we found out that there was as much electric flux into the box as there was electric flux out of the box. And so if we summed up the total flux over all of the 6 surfaces of this particular box, we would find that the total flux is 0 in this case. And that means that the charge enclosed in the box divided by epsilon 0 must be equal to 0. And epsilon 0 is just a constant. So that means that this particular case can only occur if there's no electric charge inside the box. Okay, so just by looking at this, even if we weren't able to look inside the box, we would know that there was a net charge of 0 in the box. But it's a little bit weirder than that, because this is the total charge enclosed. So I could very well have a case where I have a box and I measure the flux over the box, and in this case I might have electric field lines that are going in all sorts of directions into and out of the box. If I measured the electric flux in and out of that box and found that the total flux was 0, that means that the sum of all the charges inside the box has to be 0. But that could be satisfied by, say, having a plus charge over here and a plus charge over there, but an equal number of minus charges in there, so that these 2 charges are canceled out by those 2 charges, so that the total is equal to 0. Gauss's law applies no matter how many charges are in the box, no matter where the charges are distributed. This result has to hold, that the sum of the flux over the entire box has to be equal to 0. Let's take a case, another example. Let's just take the case of one charge in a box. So if I have one charge, one positive charge, Gauss's law would say, let's see, I know from Coulomb's law that the field lines ought to look like this. If I can apply Gauss's law and calculate the total flux coming out of that box. And just looking at it, I would say that would be a pretty complicated thing to do, because the electric field, its angle changes at different parts of the surface, and it doesn't have the same value here, same magnitude here that it has here. So it'd be kind of complicated to calculate the flux over these 4 areas. But I know that in general, if I could calculate it, I know that the total value just has to be equal to the charge enclosed in the box divided by epsilon 0. And so just by knowing what this charge is, I can use that to give me clues to what the electric field is. Or if I know the electric field and the flux, I can get clues as to what that charge is in the middle. The same thing would apply if this same charge were in an identical box, but over on the other side. The flux through this box is still equal to the charge enclosed divided by epsilon 0. If these are the same box and I've just moved the charge from one spot to another, I've got the same flux out of this box as out of this box. The convention again is it's the flux out of the box. So in each point along here, the electric field lines are coming out in the same direction as the area vectors, and so this is going to be a positive flux. If I had instead a negative charge, like this, remember that electric field lines end at a negative charge, so I would have electric field lines that are going like this, and like that, like that, like that, like that, like that. In each case, the electric field lines are going into the box. They're going perpendicular to the area vectors. And so I'm going to have negative flux into the box, and that means that the net charge has to be negative in that box. The total amount of charge in the box must have a negative sign in it, okay?